What if the bedrock of our reality isn't made of solid matter at all, but is actually a chaotic symphony of microscopic vibrations? For centuries, the history of physics has been a relentless process of zooming in. We sliced matter into molecules, broke those down into atoms, and finally smashed atoms apart to find elementary particles. But at that scale, we hit a physical wall. To see anything, an electromagnetic wave, like light, has to bounce off it and carry that information to our eyes. Elementary particles are so unfathomably tiny that the very act of hitting them with a wave of light alters their position and momentum. This is the Heisenberg Uncertainty Principle, the permanent, frustrating rule that observing the quantum world inherently changes it. Because we are completely blind at this resolution, physicists had to stop relying on microscopes and start relying on math. We were forced to invent mathematical fictions to map out a reality we'll never actually see. The most successful of these fictions is the story of the point particle. To make the calculations work, physicists decided to pretend that an electron is a zero-dimensional dot, an object taking up absolutely no space at all. This assumption formed the basis of quantum field theory. It allowed scientists to calculate and predict the behavior of three of the universe's forces: the force of electromagnetism, the strong nuclear force, and the weak nuclear force, with staggering decimal place accuracy. But the universe has a fourth force. Gravity, as defined by Einstein's general relativity, doesn't rely on chaotic quantum dots. It relies on a perfectly smooth, continuous geometry of space and time. When you attempt to cram the massive, continuous geometry of gravity into the jittery, unmeasurable quantum realm, the mathematics break down. The zeros from those point particles become divisors, and the equations explode into impossible infinities. We are left with two brilliant frameworks that refuse to speak to each other. Without a way to weave gravity and quantum mechanics together, our overarching description of how the universe operates is fractured. To bridge that gap, a new mathematical story was proposed. If a zero-dimensional point breaks the equations of gravity, the solution was to upgrade to a one-dimensional line. String theory suggests that all elementary particles are actually tiny, vibrating loops or segments of energy. Just as a single violin string can be bowed in different ways to produce different notes, these strings vibrate at different frequencies to manifest as the distinct particles we observe. The math of these vibrations yielded something highly specific. One closed loop of string produces a vibrational pattern that perfectly matches the properties of a graviton, the theoretical particle that carries gravity. Without having to force it in after the fact, gravity naturally emerged from the quantum mathematics. String theory presented a single, elegant structure capable of uniting all the fundamental forces of the universe under one set of rules. But this mathematical elegance comes with an enormous catch. If you run the equations of string theory in our standard model of the universe, they fall apart into anomalies. The theory only remains stable and consistent if it operates in a universe with exactly 10 dimensions. We experience a world with 1 dimension of time and 3 of space: up-down, left-right, and forward-backward. The math demands 6 more spatial directions that we simply cannot see. To solve this, string theorists propose a concept called compactification. They suggest that these 6 extra dimensions are folded up into impossibly microscopic geometries that exist at every single point in our observable space. The exact shape of these compactified manifolds is crucial. The geometry of those hidden dimensions physically restricts the string's movements, determining the mass and charge of every particle in our universe. To accept string theory's elegant solution for gravity, we have to accept the premise that the stage on which reality plays out is mostly invisible, curled up in dimensions we can never access. Despite requiring a 10-dimensional stage, this mathematical framework began producing astonishing secondary results. In the 1990s, physicists used string theory to calculate the exact entropy of a black hole, arriving at the precise thermodynamic formula derived by Stephen Hawking and Jacob Bekenstein 2 decades earlier. This paved the way for an even stranger mathematical discovery known as the ADS-CFT correspondence, which forms the basis of the holographic principle. The math proved that a complex 5-dimensional space containing gravity could be perfectly described by a lower dimensional boundary layer wrapped around it, a boundary that contains no gravity at all. It implies that the physics of the interior are entirely encoded on the surface. Extrapolated out, this means gravity itself and the three-dimensional reality we inhabit might effectively be a holographic illusion generated by quantum mechanics. What started as a mathematical trick to fix the equations of particle physics evolved into a framework that entirely redefines how space, gravity, and information relate to one another. But there is a glaring problem. No prediction of string theory has ever been validated by an experiment. If these strings exist, they are so small that they slip through the net of every particle accelerator and detection machine we can build. Because testing the theory directly is currently impossible, modern researchers are reverse engineering the problem. They are calculating the baseline rules of particle scattering to determine what physical conditions must exist in our universe for string theory to be the only mathematical outcome. Whether or not it proves to be the definitive theory of everything, it remains the most productive tool theoretical physicists have to probe the paradoxes of the quantum world. Human science has always relied on drafting new fictions to map out a reality we cannot directly see. Right now, string theory is the most complex, mathematically beautiful draft we have ever written.